Hi, my name is Jarin Jacob, working as technical lead for Cavium and currently working on open source data plane projects inside Cavium. So let's get started with the presentation. So this presentation is about event-driven programming model and extending the same to DPDK. So the agenda of the presentation would be like, we'll start with event-driven programming model concepts from a data plane perspective, and we'll figure out characteristics of an hardware-based event manager device it's there in the market, and we'll go over lib event dev. It's an RFC API which I sent 2 days back to the community. So we'll not go over the specifics of the APIs like prototype and things like that, but we'll go over the overall use case perspective, how these APIs can be used, and we'll go over any example use case like simple IPSec outbound processing, where how we can use these APIs in a real world use case, right? And as a recap, finally we'll go over the benefits of using event-driven programming model with respect to what we have right now. That's on the agenda part. So let's get started with the concepts first. So the event is an asynchronous notification that comes from hardware or software to core to notify that certain work is ready to process, or certain event is ready to process, or certain work has completed from the hardware. So it next need to get notified to core to start processing from there. So the typical example of events in data plane are, we treat packet from the RX hardware as an event, but it comes as an asynchronous fashion. And a crypto work completion notification from crypto hardware, where core submit a work to crypto, and when it's done with the work, crypto hardware can generate an event to an event device, and core can get the event back saying that the work has been completed, so it can go over the next set of tasks. Another classical example would be timer expiry notification event, where core can program a timer device where he can program the timeouts that so and so nanosecond or millisecond after that you need to get an event to notify a certain activity. So typically useful for tracking TCP retransmission and things like that, but that's one use case or one type of event. And CPU itself can generate an event to notify another CPU that certain session of the work has completed, so to give notification to other CPU. So typically useful in pipeline mode. So by definition, event-driven programming, it's a programming paradigm in which flow of a program is determined by a set of event that comes to the core. So that's on the concepts part. So let's look at an abstract model, how these things are aligned with respect to event-driven programming model. So we have 4 entities here, 4 components here. The left-hand side one is the events. That's I was talking about earlier, the packet event or timer expiry event or crypto events. Or software itself can generate the events called software events. And there are 3 more components in the system. One is the queues and scheduler and the cores. So the role of a queue is whenever you create or generate an event, so it gets stored in the queue. So this enqueue operation gets stored in the queue, and this scheduler can be a software or hardware-based implementation. So it runs as a component in background, and core is the one is generating a request to get an event from a queue through the scheduler. So core is going to invoke an API or something like RT event schedule. So that function go over scheduler. So scheduler looks at how many queues you have in the system and what are the synchronization methods needs to be used. That will follow later in the slides. But it go over all the queues and figure out which event needs to be taken from the queue and gives to the core. And when event gets into the core can process it. And typically a application processing may have a number of stages. If it's a like final stage, then you can send the packet back or event back to the TX hardware itself, or if it is an intermediate stage, you can send back the event back to queue through a software scheme of generation, right? So core itself can generate an event, so it goes over here. So next time you'll get the event from the scheduler. So this is a scheme what we'll call it as an abstract model. Now if you see the primary difference between the existing model what we have right now is that everything looks same, only the scheduler block is not there in the picture. So if scheduler is not there, then what's going to happen now is that core needs to have a static binding to the queues, because there is no scheduler in place. So you have to connect to core needs to connect to a queue to get a work from that. So that makes kind of a static configuration or issues with scalability part, because you have to know how many cores there in the system, and you have to upfront have to know what's the work that core needs to be given, right? Because you are connecting a core to a queue, right? So those issues will be get fixed through this schedule means, where you can automatically get a good load balancing kind of approach with scheduler, because you just ask core just ask to scheduler, and scheduler will go over the events and get the work to you, right? So that's the primary difference between abstract model. Now, so let's look at attributes of an hardware-based event devices. So we talked about abstract model. Now we need, so there are some hardware devices in the market like Cavium or NXP platform. There are a lot of hardware devices in the platform where they have a capability to deal with such a event-based programming model. So the primary difference between the abstract model and what we see in this kind of hardware is that there can be millions of flow queues. So it's not just 1 or 2, 3, like maybe not 1K, it's like millions of flow queues, right? That's a primary difference. And another thing is that it's very, so the next one is an event associated with a single flow queue can be processed in concurrent fashion on multiple CPUs while maintaining ingress order. So this part is very critical about event-driven programming model, where a single flow goes over multiple CPUs and everyone operates on parallel, and when it goes over the downstream NQ, it gets ingress order of, it maintains the ingress order. So that way application programming is very easy. You get the event, process it, and hardware takes care of the ordering, right? So that's the beauty of this kind of devices. And it provides a means of synchronization of the events without software lock scheme. So that means some session of the application processing need to do in critical section. For example, if you are considering outbound IPSec processing, per se you need to update the sequence number kind of a scheme, right, where you have to do in critical section. So those, we can't rely on software-based schemes like mutex or ticket lock or any spin lock kind of a means to have that kind of critical section. So these kind of hardware provide a means to do synchronization in hardware. We'll get into the details of that, how this is done, but this provides a means to do that. And it's typically, it's based on the priority-based scheduling, so that on the RX side, you can have a quality of service method attached to it, because you don't need to treat all events are same, right? So some of the event needs to be processed in high priority fashion. So those things will be addressed here with this scheme. And this kind of device introduce a new data structure called schedule groups. So basically, schedule groups provide a means to execute different functions on different core. That would mean that each core can be a member of any subset of schedule group. So I can say that there may be n schedule groups in the system. The core 0 can say that, hey, I'm part of schedule group 0 and 1. I need to get only event from that schedule group. I don't need to expect any event from any other schedule groups. So that way I can, in the application sequence, I can say this session of the code can be executed here, or a set of session can be executed on set of cores, or some of the other section can be executed on different cores. So it provides a means to do that. And again, there may be one-to-n scheduling groups based on the device capability. So that's one thing. And the flow queues. So earlier we talked about the queues, but when it comes to data plane perspective, it's more in line to have a flow queues, because using some scheme, hardware is going to spread the traffic and insert to the queue. So we call it as a flow queue. So it's grouped under something called schedule groups, the same thing. So, and it has a different namespace. Yeah, the code to scheduling group membership can be changed at runtimes. So this enables a load scaling explicitly from application. This is typically useful for telecom use case, where whenever you have a peak load, you can assign more cores to that set of a function, and we are done with the peak load. Maybe you can give the work back to some other cores. So everything can be done in runtime fashion, so that that scaling part will be achieved correctly in this scheme. And other use case, like in a session of processing, maybe few portion of the code you need to have a less latency. So maybe you can attach more cores to that, so that those events will be processed in high rates, right? So latency of some of the work can be reduced by assigning the more core. So these devices support this runtime changes in a dynamic fashion. So you don't need to shut down the device to get it done. So that's a major difference. And typically, event scheduler is implemented in hardware because the reasons are you may have millions of flow queues and you may have 256 schedule groups. So in software perspective, it may be very difficult to figure out or take a scheduling decisions to take from where should I take the event, right? Because first you have to find the schedule groups, then followed by you have to figure out a flow queue from where the event gets it, right? And it's going to be called in fast path all the time, right? So doing it in software, maybe you need to think in a different perspective, but typically these things are implemented in hardware. So considering the attributes of an hardware-based event device and means to have a standard application API interface to application, so that we can have a platform neutral API interface, so that these kind of devices can be used in a more natural form. We try to create an API called, or RFC API called libEventDev. So we're trying to follow existing DPDK methods like what been used in other device like Ethernet and crypto, where device identification, device configuration, or device start stop, all these things we are taken directly from the DPDK model. But we're trying to figure out what are the different components there in the libEventDev device, if you take it as a global view. So it's not very different from the abstract model, so what we talked about earlier. So I will try to say the difference between the abstract model. The first thing is the flow queues. In abstract model, we had only few queues, but in real device, it's going to be have millions of queues. So we need to have some mean to grouped under some scheme, so that you have a fine control on that. So with schedule group, it's grouped under, the flow queues will be grouped under, and each schedule group will assign a priority relative to other schedule groups in the system, so that scheduler can take the priority scheduling decisions based on the priority. So this is a one main difference. And on this side, we have the schedule group, we have a new data structure where each core is going to say a bit mask representation, where how many groups belongs to get scheduling events from there, right? So each core is going to maintain a list. It's kind of a bitmask model where you can say core 0 can get an event from group 0 and group 1 and last group, and core 1 can say maybe the first group only, right? So that like that we'll define the model so that you will have a cores will have a fine control on from where the event comes from. That's abstract model, and there are two main operations here. One is enqueue and the other one is a schedule. So enqueue operation, it's nothing but it can be done from software or hardware in transparent way because arguments is going to be same. Doesn't matter it enqueues from hardware, software. So while enqueuing to the queue, you need to provide the complete information of the event. So let's get started with the event. So first one is a group ID. So with that, we are going to say which schedule groups this event is going to go. And then we are going to specify the flow queue ID. That's like which flow queue you need to go this thing inside the schedule group. And schedule sync method. This is a synchronization method. We need to use it to enable the synchronization. So this will talk later in the slides because it's a different concept. And event type. So this is nothing but when it gets scheduled on the core, you have to know from which source the event has come from. So this event type, if the event comes from an Ethernet device and RX packet, then event type marked as a event type Ethernet. Or if it's from a crypto device, you will mark it as a crypto. Or if it is generated by the software, we may be calling it as an LCore based event. So that way application can know who's the originator for this event. And the last argument will be event itself. It's typically a void pointer so that when you get the event back on the core, you can typecast to any other useful data structure, right? So you enqueue the event and it's done with it. So core enqueue the event, or software or core hardware enqueues the event, and it's done with this, gets stored in the flow queues. And when core initiate a schedule function, scheduler go over all the flow queues and schedule group and gets an event to the core saying that this is the event with all the attributes what is being used while enqueuing it. Then once core gets the event, it takes the event and start processing it. If it's the final stage of processing, send out the packet or event over the wire. If it is an intermediate step, push back again to the queue and so that other core can get the work. So that's a model we have, and I'm trying to emphasize on the scheduler part. So each hardware may have a different schemes of doing the scheduling thing. So as an API, we don't need to dictate, or we don't want to dictate any specifics of how scheduler is going to do the work. But in general, we have some kind of schemes to mention how the scheduling looks like, or how the scheduling decisions will look like. But we don't want to dictate any specific means to have the scheduling, so that this framework can be useful for any other devices or any other event devices to leverage this or lib-event-dev RFC API. So that's on the component side. Now let's look at the flow, like as a software perspective, how this RFC APIs will get used. Now, so it's completely inspired from Ethernet and crypto device framework, what is existing in the DPDK, where you will have a northbound API where it's a normative specification, and the southbound API will have a driver framework. Through function bondage, those hardware specific functions will get invoked. So as a first step, you will have an event driver through with the function pointers, and it will get registered with event dev subsystem. And event dev subsystem is going to give you a unique device ID, so that application further can operate on that device ID. So it's just a unique number, 0 to n. So you don't need to know about anything else. So it's just a number is given by the lib event dev subsystem. So yeah, so once you get the device ID from their own, application is going to use that device ID to operate on this device. So the first thing will be the application typically does is get the capability of event device, where it's going to figure out how many schedule groups it has and number of flow queues are available in the schedule groups and things like that. So once it's know the capability of the system or the event device, it started configuring that device. So you may have let's say 256 schedule groups, but your specific application may need only say 16 schedule groups. So you can configure a device with the information what you need, what you got it from basically from the capability API. So you configure the device saying that, hey, I need 16 schedule groups and I need say 1K flow queues inside the schedule group. And just like an Ethernet API where we trying to configure the queue, right? So same fashion, we'll try to configure the schedule groups here. And you will specify what's the priority associated with the schedule group so that scheduler can take an action based on that. So once you're done with this configuration, finally, you need to connect this schedule group to a upstream event producer in the system, like Ethernet device. He's the one actually generating the event in a packet form, right? So you need to get connected this schedule group to event producer. It can be an Ethernet device or it can be crypto device. So once it's get connected, you're all set and ready to go. So configuration side is done. Once it's connected, then in fast path, hardware or software trying to enqueue to the that flow queue, that's under the schedule group. So start keep enqueuing to that queues. And then cores start in action in all L cores comes, and in while one start requesting for an event through schedule function. You request scheduler gets you a work, you start the work, what you got it. And if it's a final stage of thing, it just sends out to the TX hardware, or if it is an intermediate stage, you go back again to a different queue for processing. Yeah, so that's how it operates on. And then finally, in terms of scheduler functionality, we're trying to touch upon what are the scheduler expectation in with respect to a sane basic scheduler is available in the system. So when you look at, there are two things to figure out when you do a schedule work, right? First one is figuring out which schedule group you have to get the events from. Once you got the schedule group, we have to figure out which flow queue to get the events, right? So these two decisions has to be made by the scheduler. Hello? Yeah, so that's fine. So get back to work. So, yeah, so the two things, selection of the schedule group, that's a one primary function of the scheduler. And once it's found the schedule group, and selection of the flow queue and event associated with that, right? So, schedule group selection, basically, there is three criteria. First of all, you need to figure out how many schedule groups present in one event device. Once it's figured out how many how many schedule groups are there, then it has to figure out the caller L core membership in this schedule group. So if you look at this diagram, we are going to have a schedule group L core membership maintained here. So it trying to go over the list and figure out what's a relationship between this caller L core and the schedule group. And once it's done that, another criteria should choose that schedule group priority with respect to other schedule groups in the system. There may be different other scheduling decisions in a different hardware, but we'll take this as a bare minimum things so that application perspective, he can assume that this much stuff will be done by the hardware or software implementation. Once it's done that, you got this schedule group, now you need to get inside the schedule group to get an event, right? So that is something we'll call as a schedule sync method. That's the one you will decide to use the selection of the event, so that I will explain in the next slide. Yeah. Yeah. So the schedule sync method is the one is useful for selection for the specific event from a flow queue. So there are 3 different known schedule sync methods. So the first one is called parallel. The events from a parallel flow queue can be scheduled to multiple cores for concurrent processing, and ingress order is not maintained. That would mean that it can just use for some kind of a load balancing kind of scheme, but it cannot be used for ingress order if it needs to maintain the ingress order. Typically useful for if you have a ping packet or that kind of scheme where order doesn't matter, then you can use with that. But in data plane use cases, typically we won't use that, but in general, but it has a support for that. The next schedule sync method is an atomic. This is interesting one where event from an atomic flow queue can be scheduled only to a single core at a time. That means this enables you some kind of a critical section in the flow of a program where you want to have some section of the code, it needs to be executed in a critical section. Then atomic flow queues can be used because it's only one core it gets scheduled, right? So that means it's just only one core it gets scheduled. So by natural way, the atomic critical section will be enabled on this thing. And since it's outstanding is always 1, by default ingress order is maintained with the scheme. But this will be used only when to enable critical section in the application flow. Yeah, so the next one is the ordered one. This is the most useful one in a data plane perspective, where event from a ordered flow queue can be executed on multiple CPUs concurrently while maintaining the ingress order, right? So you get a single flow, it gets spread on multiple cores and everyone execute in parallel. And when it finally sent out to the hardware, when it sent out to a TX device, the order will be start maintaining by the hardware. So this is pretty useful in data plane perspective, and application does not need to worry about the ordering part. So yeah, so this one enables the ingress order and enables high flow single flow high throughput, because the same flow will be executed parallelly on multiple CPUs. Now let's look at how ordered flow queue maintains the ingress order, right? So different hardware may have a different scheme. Even Cavium hardware does not have exact scheme, but we'll stick to one convention so that it'll be easy for all other event device to have one scheme. And in application perspective, you can have some kind of a specification. Now this is how hardware expect to have a ingress ordering, right? So we'll take it as an example. So let's take a system where you have a 6 cores, 1 flow queue, and 1 downstream queue. It can be any type. So the left side is a flow queue. It's a single flow queue where you have a 6 events from an order 1 to 6, 1 being the first and 6 being the last. It's in FIFO order. Since we have a 6 cores running on that system, these 6 events will be scheduled to 6 cores at a time because it's from an ordered queue. So 6 of them will be start processing that in a different fashion, right? This will be start processing it. And when it enqueues to a downstream queue, it maintains order. That would mean that if the event that holds the 6th event will wait under 1 to 5 events get enqueued. Or other way to look at it, the core holds the 2nd event will wait under the first core that holds the first event to get inside the downstream queue. So that way, the enqueue function will be waiting under the order get maintains. Once enqueue is over, then you can assume that it's enqueued to a downstream queue and order is start maintaining it. So I thought of keeping as a same API. We don't need to create any explicit new APIs to maintain order. So we use the same API schedule and enqueue to enable the ingress order. We don't need to use any other API to do that. So this way, this is how we will enabling the ingress ordering of a flow queue. Okay, now let's look at a real world use case, how this scheme or event-driven programming model can be used to enable a real world use case, right? So let's take a simple use case. I choose a simple IPSec outbound use case. And if you see a simple IPSec outbound use case, you will have, if you take that system where you will have n RX ports, meaning n ports which will have RX and TS queues associated with that. And if you see outbound processing, we need to do a certain section of processing in the application, right? So the first criteria to choose what are the phases in which application need to process should be based on the synchronization method, what we talked about earlier, ordered, parallel, atomic. So that's the one application first choose what kind of scheme or how do I split my packet processing, right? So I've taken us an example here, outbound processing, so that we can go over the details on how phases will be divided here, right? So the first step, the phase one would be, before that, okay. The first, you are going to configure the RX hardware to generate a flow as much you can, because you can, if it is a IPSec processing, you can maybe configure a 5-tuple based scheme where you can create a maximum flows available in the system so that you can spread the packet as much you can. Then this comes to a phase one of the application. We call it as a policy or SA lookup. So that would mean that every packet comes from an RX hardware, it comes to the phase one of the application processing where it needs to figure out a unique SA associated with that packet. So you may use ACL lookup or any kind of lookup to figure out from a given packet what is my SA associated with that, right? Because when it comes to IPSec outbound processing, the outbound processing is based on the SA. So SA will have the information. If it's an ESP processing, it will have information like what would be my header and where should I send the packet when it gets tunneled, right? So all the outbound specific information will be stored in some kind of a table in the system, and you will index it through SA. So policy and SA will be figured out, and you will have some routing lookup. Once encryption or once you're done with crypto work of IPSec processing, it has to send to a respective or some of the ports, right? So that lookup, you will use some LPM or any kind of methods to do a lookup. The good part is this works in an ordered fashion. That would mean that if a system has 10 cores, 10 of them will be worked on that. Or if it has more than 10 queues, 10 cores, it will be start working on this. So based on how many cores it's available, everyone is going to work on this phase one, right? So that scales very well, where we don't have any binding between, hey, if I come from this port, I need to go to this core and I do this thing here, right? So that kind of scheme is not required here. So it's all come to phase one. Depending on how many cores you have, you will process there. And so U does every parallel processing here by finding the SA, route lookup and things like that. And when you reach to the point where I've done all the stuff in concurrent fashion, now I need to do something on critical section, right? This is phase 2 here. In IPSec case, it's a sequence number update where the ESP header needs to have a unique sequence number for that assay. So it enqueues to the atomic sync type queue and be done with it. Then the core is going to wait again to get a next work, right? Then when you get an event from an atomic queue, it can understand that, hey, the work has come from phase 1. So now I need to process the phase 2 of the thing, right? So typically I just increment the sequence number in the ESP header, and I'm going to submit the work or submit the packet to crypto hardware saying that, oh, I made the headers and things like that, now just encrypt this packet for me. Now you give a request to hardware, so what hardware start processing this in background. Once hardware is done with processing the encryption or IPSec work related that, it's going to post yet another event. So when you get an event from a crypto device, you can understand it's a phase 4 because phase 3 is the one generating the crypto event. So you are in the phase 4. So then core understand that, okay, you got an event from an event, crypto device, now I'm going to send that, I do a final cleanup on whatever is required on IPSec, then I'm going to send to a respective, the T export. Yeah, so that's how we divide and use the event-driven programming model in a real-world use case. Now, yeah, so I'll try to touch upon the core's view on this thing. So here the beauty of it, every core is identical here now, right? Everyone will, because it's not bound to any specific core, any specific work. Every core is identical. Everyone will have while one and do a schedule to get a work, process the specific stage. If it's done with that, enqueue back to the downstream queue and be done with it, right? So this is how we maintain it. And now let's look at a simple pseudocode perspective, how it looks like, right? So now on each core, there will be a while one, you keep waiting the schedule. We will keep waiting the events through schedule. If there is an event, it goes. If there is no event, go back again. If there is event, comes back. And if it is a event from a Ethernet device, it can figure out that you are in phase 1, and it start processing phase 1 of the application processing, where figuring out the essay, creating a packet per essay, and things like that. Once you're done with the parallel work, and when it reaches to the point where it has to do a critical section work, it enqueues to another downstream queue. So while enqueuing, you are going to specify what is a flow ID. So now thereon, the new flow is going to be SA because SA is the one you are going to process it, right? So the new flow will be SA, and there will be multiple SAs in the system. That's another thing about it, right? So there may be multiple SAs, still your existing core is going to work, right? Because you are going to have a new SA here. So we don't need to have any scheme of mapping. This flow works on this core, nothing that sort. So we just give a new SA as a new flow here and make a sync type as an atomic. And you create a subsystem event number. You can specify some application specified number. Then you enqueue it. That's be done with that. And core is again go here and start waiting it. And if you get an event from this previously enqueued one, that's like L core, and sub event type is this one, the sequence number update, you can figure out that it's a phase 2. You do a critical section processing and enqueue to a crypto hardware. And again, you start waiting on the next event, right? So then if you get a work from a crypto hardware, you send the packet out, right? So every code looks identical. So in application perspective, it's damn easy to write a code, right? Because you don't need to worry about how do you map the queues and which scheme I need to use, what flows goes where, nothing. So we just put an application logic in a transparent way in application, and rest all things will be taken by the implementation. Having said that, so this would be the last slide. So where we're trying to touch upon the benefits of using this model. The first one is like enable high single flow throughput with ordered single method, where a single flow will be get spread out over multiple CPUs and everything can be operated in parallel in concurrent fashion while maintaining the order. And the processing stages are not bound to a specific cores. So you can directly scale well, right? You don't need to know upfront how many cores are there in the system. So it's not bound to any specific stage. The scheduler is going to give the work to you, right? So it doesn't matter, your application code may not have any changes with respect to how many cores there in the system. It is going to perform well if you have more core, if it performs in lesser fashion, if it is a few cores are available. And there is a scheme of prioritizing the events to enable the QoS. So that's a benefit of it. And you will be removing static mapping between core to port, the RxQ mappings, right? Where you say that from this RxQ 0 of that port 0, I need to start processing in nothing that sort. Everything comes to scheduler based on the phases of the application processing, is keep processing that. And again, scaling from 1 to n flows also relatively easy because they are not bounding any flow to specific core. That's it. So questions? Yeah.
For the scheduler, we sure need hardware, or were there any experiments using software cores for scheduler?
Oh yeah, so Cavium has support for doing this in hardware. But the specification, we're trying to make it in such a way that there is no hardware specific element in the normative specification, so that we could have a software based implementation also for that.
So do you have any examples, heard of any examples for software scheduler?
Examples in the main, like how do you implement in software?
Yes.
Meaning, how do you implement it? Like so we have a specification for instance, you can have a ring based scheme where the flow queues will be mapped as a ring, and you will be enqueuing to the ring, and there will be a service core. You will go over the flow queues, that's a ring, and figure out the packets from there.
Okay, you dedicate one core to do the scheduling, yeah.
Yeah, that's based on the load, right? So that's another, so the software-based schemes, that's another problem, right? You will not be knowing the traffic, how much is going to come, right? So, so you may need to assign a number of cores based on the traffic that comes to the system.
So,
no, so this is just an RFC right now. So I think we are discussing with Intel folks also to see how it can be implemented. And I'm not sure like if they have any FPGA or any other means to do that or not. But as typical, this will be typically useful in a networking SoCs like NXP or Cavium, where things are not very much bounded to the Rx port of the system, right? So more scheduling fashion. It's just a new way of doing the stuff if the hardware has support for that.
So in this scheme, you have packets, so segments from a particular flow going to multiple cores, right? So, and to maintain the ordering, you want all of those packets to process at the same time, right? So, will the flows with larger packet sizes or larger number of packets which need to be processed?
Yeah, so even if it is a segmented packet, so it's like, so how do you go? It's like if you're going to follow the MBUF structure itself, right? So the event, it's going to be a MBUF.
Mm-hmm.
Okay, then you will connect n number of downstream MBUF associated with that, but the parent MBUF will be the event, right? So even if it has more segments, it holds that thing, right? Everything comes through as a single packet or even event.
Oh, so okay, so all the segments of one packet is one event.
Yeah, because we're going to map an event to a MBUF. If an event belongs to a packet, we'll make it as a MBUF.
Okay, so all segments will be then processed by just one core.
Yeah.
Okay.
Right.
Okay.
Yeah, so I'm quite intimately acquainted with your product. I've worked on some few generations on it. I had a question though. when you showed the mapping of flow queues to groups,
Right.
right? So when the core asks for a packet from a particular group,
Right.
is it possible to prioritize amongst the flow queues within a group, not amongst groups, but within the flow queues within a group?
Yeah, because the problem is if you take that scheme, if you have a millions of flow queues, how do you enumerate that, right? It's going to be a different thing, right? Yeah. So that's why we're trying to make it as a schedule groups as a priority stuff and group flow queues under that, right? Because million flow queues, you start enumerating how many, what's the priority associated with a flow queue, it's going to be difficult while configuring it.
Yeah, well, I'll talk offline, we have some needs, but secondly, sometimes in order to maintain our, or to maximize the use of our cache, right, in the cores, we want to dictate which flow exactly to process next.
Right.
So what kind of control do you have for
so
that case?
it's part of the specification actually. I didn't talk about because of a timeline, so maybe I can. So we have some means of enabling run to completion support. So where I need to dictate that even though I enqueue a queue to a flow queue, I don't want to go over that event to any other core. I need to get over the same core so that I can use the L1 cache or cache related.
Right. So let's say I'm processing some tables, right? I'm going to look up some tables. So I would prefer that if there is traffic for what I pulled in last into my cache, right? Or let's say some flow structure, right? I would like to process the packet for that flow itself, as long as there are packets for that flow. So
you're saying how that lookup can be done? Or?
Yes. Is there a mechanism?
That's the beauty of it. So when you get an event, where is that? Yeah. So when you get an event, basically, if you see, there will be the sub event ID and the flow queue ID will be there, right? So that you can treat it as a unique numerical number from 0 to n, right? So that you can have a used for lookup for a downstream stuff, right? So it's a number from 0 to n, right? So that can be used for looking up.
Okay. Lastly, you also, I think, touched upon the way in which you can parallelize the processing and still maintain ingress order amongst flows, right? Now, does it work in the case where for some of those parallel paths, right, you need some atomic operation in the middle, but not for all of them, right? So let's say, again, going to the concept of a flow, right? Let's say we have a flow, and for some of those packets based on the content, you want to do some operation, but not for all of the packets. In that case, is it possible to maintain the order, ingress order, where some flows follow a different path and some packets of the flow follow a different path from other packets of the flow?
Now, so obviously order will be maintained if all go through the same path, right? If we are breaking in between, then there is no concept of.
Right. So there is so basically there will be some packets.
So why you are breaking from the flow that this is going to be a different flow, right? Then you are treating this as a differently, right? Otherwise you would have put over the same chain, right, to go over, right?
Yeah, but there are only some packets that are of interest for you to do those special operations. Others, you don't care. You don't want to have the overhead of those.
Then you have to maintain the order while it goes out.
Yeah, in this scheme that you described, will it maintain the order?
No, if it so every events, if it follows the same chain, then order will be maintained. Like in this case, if everyone is get enqueued to this point, right? So that means here order will be maintained. Right. If you're not enqueuing there, then we can't.
Then you won't.
Then we can't. We can't. No one can.
Flow when you know that the packet of whatever you're looking to separate them, can't you make it another flow?
Yeah.
Yeah, you can do the different functions. What I was saying that he can make it as a different flow when he knows that there will be some criteria to process the packet differently. You can classify them in different flows in the beginning. Then both of them will have the separate tags.
Yeah, the issue becomes that if that flow then have to subclassify into separate kind of subflows within that, and then that will break the ingress order.
No, and in the beginning, when you were classifying the tag itself, the hashing mechanism at that time, if it's a port or TCP something, you can have the different hash for both of, and it will separate them as two flows.
We probably need to stop there and take a break. Well, Jaren will be in our panel session later, so there'll be opportunity to ask further questions on this later.